In this video, I'm going to show you how to find the area and perimeter of composite shapes involving circles and semicircles. For example, this shape here is composed of a square, right here, and a quarter circle on the left side here, and we want to find the perimeter. The key to this problem is to use what we know about squares and quarter circles to label some of the other parts in this diagram, and that'll help us find the perimeter. So first of all, we're given this side here of the square. It's 6 centimeters, and we know that a square has 4 equal sides, so each of these sides are all 6 centimeters. So let's label them. So this side here, from here to here, that is 6 centimeters. Likewise, this side here is 6 centimeters. That's one that we had labeled already, so we'll leave it. And then this side here is 6 centimeters, and we'll label that. And this side here is also 6 centimeters, but that's not actually included in the perimeter of the full shape. That's on the inside of the shape, so we're just going to leave that as is. Okay, so now it just remains to find this side here and this side here. Okay, but we knew this side was 6 centimeters, and it's a radius of the circle. This here is a radius of the circle, so that means the other radius of the circle also has to be 6 centimeters. So that means this side here is also 6 centimeters. Okay, and then what's left? Well, we've got this side over here. But let's not worry about that just yet. Let's take inventory of what we have so far. So the perimeter is just all the sides added up. And right now we can add up all these straight sides. All that's missing is a curved side. So let's add up all the straight sides. The straight sides, those add up to, well, each one is 6 centimeters. And then we have 4 of those, 1, 2, 3, 4. So 6 times 4 makes 24. Okay, so that's our perimeter of the straight sides. And now how about that curved side? We know that this curved side corresponds to a quarter of a circle. This is a quarter of the exterior of the circle. And the full measurement of the outside of a circle, that's just the circumference. So this curved side here is just going to be a quarter of the circumference of this full circle. So let's write that down. The curved side, that is 1/4 the circumference, 1/4 times circumference. And from previous knowledge, we know that the circumference can just be expressed by 2 pi times the radius. So 2 pi r for radius. And the radius, we have a measurement right here. That's just 6 centimeters. That's the length right here. That's just 6 centimeters. So we can plug that into our circumference. So 1/4 times 2 pi times 6. And we'll do that multiplication. 6 times 2 is 12, and then divided by 4 is 3, so that's just 3 pi. Okay, so that's the length of the curved side. The curved side is 3 pi centimeters. And now we're in a good position to find the full perimeter. The full perimeter is just the sum of all the sides, so we can add the two results that we got from before. We just have 24, then plus our 3 pi. And let's put some units on that because it's our final answer, and we need units. Units is centimeters all throughout, and perimeter is just linear units, so that just stays as centimeters. So this is our full perimeter. Now this is the exact perimeter, and it can't be simplified anymore because pi is just an irrational constant, but we can approximate this a little bit. Using an approximation for pi, we can write this as, this is approximately 24 plus 3 times 3.14 centimeters. 3.14 is our approximation for pi to the nearest hundredth place. And if we punch that into our calculator, then we find that that is roughly equal to 33.42 centimeters. So this is a decimal approximation of our full perimeter. It's not exactly our full perimeter. It's just rounded to the nearest hundredth place. But it gives us a nice decimal number so that we have a better intuitive feel for how big this perimeter is. Here's another example, except this time we want to find the area of the shape. The shape is composed of a triangle right here and a sector of a circle, a 150-degree sector right here. So how are we going to find how much space this shape occupies? Well, we can break this up into two subproblems. We can think about finding the area of the triangle right here. Let's say that's area of triangle, and then we'll figure out what that is. And then we can also find the area of this sector. And let's write that right about here, area of sector. And we'll figure out what that is. And then the full area will just be adding these two areas together. That's how we get the full area of the shape. Okay, so first of all, the area of the triangle. Area of a triangle, remember from before, we already know that's a half times the base times the height. So now we just need to figure out what are the base and height for this triangle. Well, we're given the height here. The height is very clearly marked. It's just 4 centimeters. So let's put in 4 for the height. And we've got a half here. And then what is the base? So the base is this distance here. Now notice that this is just a radius of this sector of the circle. And over here we have that the radius is marked as being 6 centimeters, and the radius has to be the same on for the whole circle. So this side here also has to be 6 centimeters. So that means the base of the triangle is 6 centimeters, and then we can just find the area by doing a half times 6 times 4. Well, a half times 6 is 3, then times 4 is 12. So the area is equal to 12. Okay, now how about that sector of the circle? So the area of a sector of a circle is just a portion of the area of the full circle. So let's start out by writing the area of the full circle, and we're going to take a portion of that. So area of circle, and what portion should we take of that? Well, we want 150 degrees worth out of how many degrees total in a circle? Well, 360 degrees total. So that gives us the portion. Out of the 360 degrees in the circle, we want the area spanned by 150 degrees. So area of the sector is 150 divided by 360, that fraction there, times the area of the circle. And then we can go ahead and simplify and compute the area of the circle. So first of all, this fraction, let's simplify this a little bit. So divide top and bottom by 10, we just get 15 over 36. You can cross out the zeros. And then we can think about, let's divide top and bottom by 3. So 15 divided by 3 is just 5. And then 36 divided by 3 is just 12. So this fraction reduces to 5/12. And now the area of the circle, we know that formula is just pi r squared, where r is the radius of the circle. And we know what the radius of the circle is. That's just 6 centimeters here. So let's plug that in. So equals 5/12 times pi times 6 squared. So that's equal to 5/12 times 6 squared is just 36. So times 36 pi. And then we can cross cancel here. Divide by 12, that's 1. Divide by 12, that's 3. So then just 5 times 3 pi, and that's 15 pi. Okay, so we've got the area of the sector, and we've got the area of the triangle, and now we can just add them together to find our full area. So our full area is just the area of our triangle, 12, plus the area of our sector, 15 pi. And don't forget units, because that tells us what we really mean in a physical sense by this number. Our units are centimeters, so area is two-dimensional, so centimeters squared, square centimeters. So that is our full area. And to get a nice decimal number, we can approximate this area using an approximation for pi. So that's approximately equal to 12 plus 15 times approximation for pi is just 3.14, and then centimeters squared. Keep our units at the end. If you punch this in your calculator, then you'll find that's equal to 59.1 centimeters squared. So this is also an approximation that we can use for the area. That's the true area, that's the approximation. Here's another problem that's pretty similar to the previous one, but this time we want to find the area as a function of r, which is the radius of the semicircle. So we want to carry this constant r through our computations. But we're going to approach it in the same way. We see that the shape is composed of a semicircle and an isosceles right triangle, so we're just going to break it up and compute the area of these two shapes separately. So first of all, let's look at the semicircle. We'll shade that in red, and then we'll write area of semicircle, and we'll find that. But let's take inventory of the other shape also. The other shape is the triangle. We'll put that in blue, and then let's write area of triangle below here. So we're going to find the area of the semicircle, we're going to find the area of the triangle. We'll find them both in terms of r, the constant. We'll just carry that through our computations, and then we'll find the total area by adding both of our results here. So first of all, looking at the area of the semicircle. So area of a semicircle, well, that's just a half the area of the full circle, because semicircle is half the circle. So a half times area of circle. And area of the circle, we know a formula for that. So it's a half times area of circle is just pi times r squared. And there is our constant r. We're just going to leave that as is because we want the area as a function of r. So that's all we have to do to find the area of the semicircle. So now we're on to finding the area of the triangle, and this one's going to be a little bit trickier. But let's write down our formula. So area of triangle, that is just a half times base times height. So half base height. But the issue here is that we don't actually know the height of the triangle. That's going to be a little bit different to find. So let's look again at the information that we're given about the triangle. We're told that it's an isosceles right triangle. So why don't we make use of that information? Isosceles. That means its two sides are the same. So why don't we just label the sides? We'll say that each side has length s. And because this is a right triangle, we can also interpret this triangle as having this as the base and this as the height. It's really just half of a square. So the area is just a half times s times s. S can be our base, this s can be our base, and that s can be our height. A half times s times s, which is just a half s squared. But we're not done yet. We just introduced s to clean things up a little bit, but we still need to write this in terms of r. So we need to figure out what is the relationship between s and r. And we can do this by using something that we knew from before. We know that an isosceles right triangle has the following ratio of side lengths. Has the ratio of 1, 1, square root 2. So if these legs are unit length, then the hypotenuse has to be square root 2. Now that's not necessarily the dimensions of this triangle, but we know that the sides here have to have that same ratio. So let's draw a diagram of our triangle next to the one that we've just drawn. Our triangle has, well, its hypotenuse is twice the radius, the diameter, which is just 2r, and its side lengths are s. So what we can do here is we can say that these triangles, because they are similar, their ratio of side lengths has to be the same. The ratio of the hypotenuse to the leg here in this triangle has to be the same as the ratio of the hypotenuse to the leg in this triangle. The ratio of the hypotenuse to the leg in this blue triangle, well, that's just 2r over s, and the ratio of the hypotenuse to the leg in the other triangle is just square root 2 over 1. So here we've got a proportion, an equation that we can use to figure out what is s in terms of r. So let's solve this equation. So we'll start by, let's multiply both sides by s to cancel out that s from the denominator. So we have that 2r equals, well, square root 2 over 1 is just square root 2, and then multiply that by s. So 2r equals root 2s, and then we can divide both sides by root 2 to get s alone on its one side. So we have 2r divided by root 2 is equal to s. And we can simplify this a bit by just multiplying by root 2 over root 2, and then we get 2 times root 2 times r over root 2 times 2 is just 2, and that's equal to s. Cancel out the 2's, and we just have root 2r is equal to s. So we're going to use that bit of information to actually express our area of the triangle in terms of r. We're going to substitute for s here, write it in terms of r. And we get that the area of the triangle then is just a half times s squared, while s is just root 2r, so a half times root 2r squared. And now we just simplify that, so that's a half root 2 squared is just 2, so half times 2, and then r squared is just r squared. So a half times 2r squared, the half and the 2 cancel out, so we just have r squared. Nice, so we've got our area of the triangle in terms of r, that's just r squared, and we've got our area of the semicircle in terms of r, just a half pi r squared, and so now that positions us nicely to find the full area. We just have to add them together. So the full area we get by just adding the two results together. So a half pi r squared, and then plus our r squared here. And we can factor that a little bit to make it more clean. That's just equal to, let's factor out a half and an r squared. So a half times something in parentheses times an r squared. When we factor that out from the first term, well, there's just a pi here, because we've got a half r squared, so just a pi. And then the second term is r squared, so we factor out an r squared, then we just got 1, and then to factor out a half, we have to turn that into 2. So plus 2. So a half times pi plus 2 times r squared. That is our full area. So the takeaway of these problems is that if you want to find the area of some composite shape consisting of simpler shapes like this one, then all you have to do is you can break it up into just the sum of areas of the simpler shapes. And then you can just compute those areas of the simpler shapes separately and add them together at the end, and maybe simplify your answer a little bit to clean it up nice, and then that's all you have to do, you're done.